I'm going to start with the extensions to IPsec for post-quantum cryptography, but note that I will only cover the extensions for making the IPsec key exchange quantum safe. Today, I won't cover the extensions for making IPsec authentication quantum safe. Making IPsec authentication quantum safe is very closely related to making PKI, or public key infrastructure, and certificates quantum safe, and this is a much more complex and broader topic, which I could perhaps cover in a future webinar. Also, even though the first NIST standards to authentication have been published, the relevant standards in ITF, as well as commercial implications for making authentication quantum safe, are both still a work in progress. In August of 2024, so not that long ago, NIST published a standard which is called FIPS 203, which is the standard for the first quantum safe algorithm to replace quantum vulnerable Diffie-Hellman. The name of the new algorithm is Module Lattice Key Encapsulation Method, or ML-KEM for short. And you may know it by a different name, namely CRYSTALS-Kyber, which was the code name that was used during the standardization process. Now, ML-KEM in very broad lines works as follows. Alice, on the left here, performs a so-called key gen operation, which generates a public key, PK, and a secret key, SK. Alice then sends the public key to Bob and keeps the secret key. Bob performs what's known as an encaps operation, consuming the public key that he received from Alice and generating two things, namely a clear text CT and a shared secret SS. He keeps the shared secret SS and sends the clear text back to Alice. And finally, Alice performs a decaps operation that takes the secret key that Alice kept and the clear text that she received from Bob to perform a decaps operation and generate the same shared secret SS that Bob has. These operations are based on a mathematical problem which is known as the module learning with errors problem. Right? This is different from Diffie-Hellman, which used factorization. There's a strong belief that it's computationally infeasible for an eavesdropper, for Eve, to reverse engineer the shared secret from these publicly communicated values, even if Eve has a quantum computer and even if Eve can run Shor's algorithm. Now I will look again at the same IPv2 exchange that we saw before, and we'll see how it has been extended to support post-quantum cryptography. The relevant RFCs that you can read for yourself are listed here on the right of this slide. The first change is that the Diffie-Hellman group payload that we saw before has been generalized and has been renamed to key exchange method. This is a backwards compatible change in the sense that it's just a renaming. When a Diffie-Hellman group is negotiated, the binary representation of the payload doesn't change at all. As we can see in the highlighted messages here, IPsec still does a traditional Diffie-Hellman key exchange, even if PQC is enabled. And the reason for this will become clear in a minute when I talk about fragmentation. When PQC is enabled, IPsec typically does additional rounds of PQC key exchanges in addition to the traditional Diffie-Hellman exchange that we saw on the previous slide. In other words, IPsec typically does a hybrid key exchange when PQC is enabled. There are new transform types for these additional rounds of key agreement. In this example, we see that there is one additional key exchange protocol being negotiated, namely ML-KEM 256, which is highlighted in red here. Note that there is no corresponding PQC key exchange payload in the IKSA init message. There's only a key exchange payload for the traditional Diffie-Hellman exchange, which I repeat here by highlighting it in green. The reason for this is that PQC keys, PQC public keys, are much larger than traditional keys. In fact, they are so large that they don't fit in a UDP packet without fragmentation. Now, IPsec has its own fragmentation mechanism, but IPsec does not allow the first IKSA init message to be fragmented. And for that reason, the PQC key exchange, the public keys, are moved from this message to a separate follow-up message. There are two new IPsec RFCs that have been introduced to allow for these additional rounds of PQC exchanges after the initial round of Diffie-Hellman key exchanges. RFC 9242 introduces a new message type, which is called IK intermediate, which is shown here. And RFC 9470 describes how this new message type can be used to do multiple rounds of hybrid key exchange. So in this example, we see that there's one additional IK intermediate exchange for the extra single round of PQC key exchange using ML-KEM. The key exchange payload in this extra IK intermediate message is used to carry Alice's public key and Bob's clear text, which we discussed earlier when we discussed the ML-KEM algorithm. Since this public key is too large to fit in a single UDP packet, we see that this IK intermediate message is IK v2 fragmented. And also, the last detail to note is that the IK SA init message contains notifications to negotiate the use of this new intermediate key exchange feature and of the existing fragmentation feature, both of which are needed to make this work.